In this paper, we present a consensus-based approach to performing sim and real reinforcement learning for manipulation. Learning from the simulation is safer, cheaper and faster, while learning from the real world is more dangerous, expensive and slower. However, in many cases, the simulation cannot mimic the real world very well, which limits robots' performances in the real world. To overcome this difficulty, we develop a sim and real training method to balance the relationship between the simulation and the real world. A consensus-based sim and real deep reinforcement learning algorithm, also called the CSAR method, is proposed for manipulator pick-and-place tasks. By applying consensus-based training, the proposed method saves training time and reduces the number of required real robot training steps while maintaining a comparable suction success rate, which is cost-effective. Using 3D cameras, we capture RGBD images from both simulated and real environments simultaneously to generate depth and color heat maps of the scene, which are fed into the suction network to anticipate pixel-wise best suction positions. The suction net consists of 5 parts: ResNet 18, batch normalization, ReLU, convolution, and upsample. After performing predictions in both simulation and the real world, consensus-based training is applied to the training parameters of each simulated or real agent. These are our training strategies and metrics. When applying the sim and real strategy, the suction success rate of the real robot outperforms the sim to real strategy. Since our policy for each robot is greedy deterministic, a robot may execute the same action repetitively if there is no environment change when using the sim to real training strategy. However, by applying consensus-based training, the simulated agent can be used to introduce noise indirectly into the sim and real environment, which prevents robots from getting stuck in the same action. Therefore, applying the sim and real strategy leads to a faster training speed, which saves real-world training costs. A striking observation from our experiment is that the best obtained policy trained in simulation is not the best pre-trained model to start the co-training between simulated and real robots. When the suction success rate of the pre-trained simulation model is 0.5, the sim and real strategy achieves the best performance. When the suction success rate drops to 0.3, it takes longer for the real robot to solve the task. Surprisingly, when the suction success rate of the pre-trained simulation model is too high, the performance deteriorates. This observation suggests that the mediocre policy is the best for co-training, which reduces real robot training costs and saves the pre-training time in the simulation. Readers may wonder why we use 3 sims and 1 real during training. Therefore, as shown in the videos, we vary the number of sims when using the sim and real strategy. More simulated robots participating in the proposed framework can accelerate the training speed and exhibit good robustness in the sim and real environment, thus decreasing the number of required real robot training steps. The CSAR approach is also capable of generalizing to novel objects. After training on cubes in both simulated and real environments, the CSAR training model can also be applied to pick-and-place novel objects such as cylinders and irregularly shaped objects with different heights. For more details, please check out our technical report. Thank you for watching.